Hey there, astronomy. We are halfway through chapter 5, and we're going to work on podcast 5.2, which deals with Einstein and relativity. Now, in class the other day, you guys watched a video about Einstein's theory of relativity, and it was a little different. Okay, so just hang with me. All right, so Einstein, you guys all know him. He's this guy with the crazy looking hair here, right? And he was around from 1879 to 1955. And he did a lot of work with math and the laws of motion by Newton. And he said, he found out that Newton's laws were good, but they weren't 100% correct. Okay, so what did he do? He began thinking about how moving observers see events around them, and he came up with a theory of special relativity, and then he revised the understanding of gravity and came up with the theory of general relativity. All right, so the special relativity has two postulates, and he said that with the first one, that observers can never detect their uniform motion except relative to other objects. Okay, so if you're moving in, well, let's think about it. This isn't a picture that I want you to look at just yet. Okay, so think about it. If you've been sitting in a car, if you're sitting in a car at a red light and there's another car sitting next to you, or if you're on a bus and there's another vehicle next to you, or, it doesn't matter. And you think that the other vehicle next to you is, creeping away. You start to see it move, but then you realize, holy cow, it's not them moving, it's us moving, and they're actually sitting still. So that's kind of what this is meaning. Okay, so think about if you were on a spaceship, just as these two folks here are in space, and one spaceship starts to move towards you. You're kind of moving past each other, and you realize that this guy here, he says it's obvious you're moving. I'm not. I'm staying still. And then this lady says, no, I'm not moving. You're moving. I'm staying still. Okay, so what we're realizing is that the other, they think that the other one's moving, and they realize that there really is no thing as anything staying completely still and motionless. So there is this thing called absolute motion through space. However, there's not an experiment that can be done to detect this absolute motion. And so that led Einstein to come back and restate this postulate, or say that it's equivalent to saying the laws of physics are the same for all observers, no matter what their motion is, as long as they are not accelerated. All right, so uniform motion up here in the first one, this uniform motion here, and then the fact that they are not accelerated here, that's pretty important. Okay, because if the spaceships were to fire off their rockets, their velocity is going to change, and the crew inside is going to feel that acceleration because it's going to push them into the seat. Okay, so the accelerated motion is going to be different, and if you were piloting the ship, you would be able to tell which ones are accelerating and which ones are not. So uniform here means that it's unaccelerated or not accelerated. Okay, so that's very important, and that's why it's called special relativity. All right, well, that led to his next postulate, which says that the velocity of light, c, is constant and will be the same for all observers, independent of their motion. So let's say that again. Speed of light has to be constant for all observers, no matter how you're moving. All right, so okay. Well, let's look at that a little bit more. All right, the two postulates of special relativity, they have, it says amazing consequence. There were some insights that was given to him, Einstein, while he did this. And he said, first off, Newton's laws will only work with small distances and low velocity. And he said, once you get into these large distances and the high velocities, you have to use relativistic physics instead. Okay, so example, he said the observed mass of moving particles depends on its velocity. The greater the mass, the greater the velocity. The greater velocity, the greater the mass. Well, at lower velocities, it's not significant. When it starts to get really important is as the velocity starts to reach the speed of light. He also said that relativistic equations describe energy of moving particles, and it can predict the energy of motionless particles if it's not zero. So here we go. We've got this. Assuming that a light source moving with a velocity v relative to a stationary object. This is supposed to all come up together. There we go. All right, so this special relativity, talking about the speed of light and seeing the light as a stationary observer. Well, if you've got here and you've got the light source is here and it's moving in relation to somebody who's sitting here and moving along with it, it's going to look as if the light source is not moving. It's going to look as if it's staying still. However, if the light source is not moving, or if the light source is moving and the observer is staying stationary, they're going to see that there's an angle. That the light seems to be coming at an angle instead of coming straight on. They can tell that either they are moving or that the light source is moving. The other thing is moving. Okay, we also know that the speed of light is the same for all observers, which means that your change in t, your delta t and your delta t prime have to be different. Okay, so you can come through and do this whole Pythagorean theorem, and we're not going to do this, so don't worry. But this is what they call time dilation. This is how you can see the delaying of time. You can see how things are moving through space. Okay. Other effects that have come about with special relativity is the length contraction. So as we saw in the video, if something is moving extremely fast, the object will appear to be kind of smushed, right? Okay, relativistic aberrations is where the angles are going to be distorted, and then the energy of a body at rest is not zero. Okay, you'll be able to find out that the energy of a body at rest, and this is the ever so famous equation that everybody knows, where E is the energy, M is the mass of the particle at rest, and then C is the speed of light. So you'll be able to tell that even though it's at rest, it's still not completely 100% still. It's not motionless. Okay, and this just shows you the high velocity electrons. They're going to have a higher mass. So as you increase the mass, you're going to increase the velocity as they're moving. All right, so after he did this, let me come back to this real quick. This right here and this right here are going to show you that mass and energy are related. And as we get into some later chapters, we'll be able to see how nature itself uses mass to convert to energy or energy to convert to mass and vice versa. All right, so general relativity. Einstein came up with a new description of gravity, and he used this because he said, look, not everything is not accelerated. There's a lot of things that are accelerated. We can't think of it in terms of special relativity, so let's pull this general relativity together. And he said, hey, look, new description of gravity. So if we take an astronaut or a person and we stick them inside of this spaceship, and it doesn't have any windows because he's right here. Okay, there's no windows. It's a windowless spaceship, and it's takes off. Well, because it's windowless and there's nothing to relate their position to, there's nothing relative to compare to, then the person inside is not going to be able to distinguish between the force of gravity and the inertial forces produced by acceleration of the spaceship. Okay, so here it says observers cannot distinguish between inertial forces due to acceleration and uniform gravitational forces due to the presence of massless bodies. Okay, so they can't tell if they're moving because they're moving or if they're moving because of gravity. Okay, well, why is that important? Because, well, let's think about it. All right, gravity and acceleration, this shows us that the two are related, and it led us to this equivalence principle. Okay, and the importance here is the description of gravity. So what they said was gravity, inertia, and acceleration are all related or associated to the way that space is related to time, and they refer this as the curvature. All right, so imagine this light source is on a board of rapidly accelerated spaceship. If you are moving, if you're staying still here and you're on the outside and you see this light source, you'll be able to see that the light source has actually moved. And it looks like the light source is staying straight. Okay, but here the person is on board the spaceship. It's actually going to give them a chance to see. It's going to look like this is, that light's being bent. Honestly, it's looking like it's being bent. So, so for the accelerated observer, the person that's actually moving, the light ray appears to be bent downward. Okay, and this says we can't distinguish between inertial effects and the effect of gravitational forces. So a gravitational force is equivalent to the inertial force must also be able to bend light. All right, and then it says this bending of light by the gravitation of massive bodies has been observed. All right, so what does that mean? Well, all right, so all of this is saying that mass tells space-time. Okay, we know that space and time have been put together as space-time, and it tells it how to curve, and the curvature of space-time tells mass how to accelerate. Okay, so we feel gravity because Earth's mass causes the curvature of space-time, and the mass of your body responds to that curvature by accelerating towards the Earth's center. And it says that all masses can cause a curvature. The greater the mass, the greater the curvature. So think of curvature as gravity. Okay, so the bending of light has been observed, and it was observed through two major experiments, and one of them was actually they looked at during a total solar eclipse, which kind of cuts off the majority of the light coming from the main part of the sun. You still have the light coming from the sides, and it's not good to look at it, but they said, hey, guess what? Curved space-time near the sun, right here, it was able to deflect the light from a distant star. And so if we're here on Earth, this light coming from this star that's just right going to be on the outside of the sun, we wouldn't be able to see it here, but it actually looks like it's coming from the side. So it's shifting the true, it's not in the true position, and we see it somewhere other than where it really is. Okay, and here's the curvature of space-time. All right, so other effects of general relativity we have is Kepler he noticed that Mercury went around in its orbit, and it did a precession. Let's say this again. Its orbit precesses, which means there's a slow change in the direction of the orbit. And they came up with 5,600.73 seconds of arc per century is where it goes off. And Kepler noticed this and found out that it was 43.11 seconds of arcs per century faster than what was predicted by Newton's laws. Okay, and it's produced by a gravitational pull of Venus, Earth, and all the other planets. And each time it returns, Mercury returns to perihelion, which is its closest point to the sun. It's approximately 18 miles past the predicted position it should have been when Newton came up with this. Okay, so what happened by this? Well, this tiny effect shows up with some serious problems when we're talking about Newton's description of the universe. So Einstein applied the principles of general relativity and calculated that the sun's space-time curvature, they calculated that the sun's space-time curvature was due to its mass and predicted its cause of Mercury's orbit to advance by 43.03 seconds of arc, which I just said earlier, it's really close to the actual one, which is 43.11. And he used his general relativity theory to calculate this and predict it. And he also came up with this gravitational redshift, which says that light from sources near massive bodies seem to be shifted towards longer wavelengths. So, the sun is a massive body, and any light that's coming from out there is going to be shifted towards these longer wavelengths instead of those shorter ones, which would be near the blues and the purples. Okay, that was a lot of stuff right there. I hope y'all got it all, and I'll see you in class.